Hello and welcome to this video tutorial on non-invasive biomarkers measurement by electromagnetic means. I am Carlos Juan from Miguel Hernández University of Elche. In this video tutorial we will discuss the measurement of biomarkers by electromagnetic means in a non-invasive way. The video tutorial will be divided into two parts. Part 1 will describe the general concepts and basic theory of this measurement approach, and in the second part we will see some practical aspects for real implementation. So let's get started. This is the general index for the whole video tutorial. The two first points will be covered in part 1, describing the basic theory of this measurement approach, and points 3 and 4 will be covered in part 2, describing the practical aspects for real implementation. So the first question we need to ask is, what happens when we apply an electric field into a piece of matter? When we apply an electric or electromagnetic field into a certain material, this interaction between the field and the material will indeed depend on whether the charges are free or bound, forming dipoles. For free charges, we have a displacement of the charges that results in an electrical conductivity. If the system is composed of dipoles, what we will see is a rotation of the dipoles that will try to align parallel to the direction of the field. This rotation of the dipole is described by a physical parameter that we call permittivity, and it is a complex parameter. So we will talk about the complex permittivity. Both magnitudes, the conductivity and the permittivity, the values of these magnitudes will indeed depend on the composition of the medium. They will indeed depend on the kind of molecules and atoms that we have in this piece of material. And this means that we can analyze the dielectric spectrum, that is, the values of these parameters, the values of the conductivity and the permittivity throughout the frequency range, and thanks to this behavior, we can identify the chemical composition of the medium. And thanks to these principles, we can propose the use of permittivity sensors as composition sensors. Let's see it in a more graphical way. So imagine that we have a system of dipoles, which would be true for a polar material such as, for example, water. The dipoles are aligned randomly in the absence of any electric field. But what happens when we apply a static electric field that is pointing constantly to the same direction? Well, the result is a rotation of the dipoles to align parallel to the direction of the field. This is true for a static field that is always pointing to the same direction. Now, what happens if we apply a varying field, a field in which the direction of the field is changing from one side to another side at a constant pace? Well, in this case, what we will see is a constant rotation of the dipoles in order to align parallel to the direction of the field at each specific moment. And now, let's go to the next level. What happens if we apply a varying field with increasing frequency? That is a field the direction of which is changing from one side to another side, and the speed of these changes of direction is getting faster and faster and faster and faster and faster. If the field is changing its direction faster and faster and faster and faster, what we will see is that the dipoles will rotate faster and faster and faster and faster and faster. There will be an increase in the rotation speed of the dipoles, and they will try to align parallel to the direction of the field at each moment, making faster and faster and faster rotations. And now my question for you is, do you believe that this behavior can be kept up to infinity? Well, the answer is no. We can increase the frequency of the field up to huge values. We have technology to do that. But matter has its properties, and the materials have their limits. So there should be a limit. There must be a limit. There must be a point in which the dipoles will just no longer be able to rotate faster. At this point, the field will be still present, the field will be still changing its direction, but the dipoles will no longer be able to follow these fast changes. The dipoles will no longer see the field, will no longer be impacted by the presence of the field, and then the dipoles will align randomly again due to thermal motion, as if it was no field, but there is field applied to this material. At this point, it is happening what we call the dielectric relaxation. The dipoles relax and do not feel affected by the field, even though the field is still active. Well, this phenomenon is really interesting because it depends on the kind of dipoles and molecules. So analyzing this dielectric relaxation, we can identify the kind of material we were applying the field into. This behavior has been modeled from a mathematical point of view. The permittivity has been defined as a real part and an imaginary part, and this complex permittivity has been defined as a sum of dielectric relaxations that occur at different frequencies. And in this video tutorial, I would like you to focus on the relaxations happening in the microwave frequency range, which are of great interest for analyzing the medium composition and which are of particular interest for biomedical applications. So here we can see the evolution of both the real and imaginary parts of the permittivity of a material as the frequency of the applied field increases. We can see in the blue line that for the real part, the values of the real part of permittivity are high before the relaxation and they get low after the relaxation. The material evolves from being highly polarized at frequencies lower than the relaxation and weakly polarized at frequencies higher than the relaxation. And in this context, we define the loss tangent, accounting for the losses in the material, as the imaginary part of the permittivity over the real part of the permittivity. So we can see how the analysis of these dielectric relaxation processes can give us information about the medium composition. So we are interested in using or developing measurement instruments to analyze these dielectric relaxations to retrieve the dielectric permittivity of the material. To that end, there are several available options and technologies that we can use, and the choice is wide depending on the particular frequency range we are interested in and other constraints of the application. We can select impedance spectroscopy techniques, open-ended coaxial probe techniques, transmission reflection line methods techniques, etc. But today, I would like to bring into your attention the use of microwave resonators. Paying the cost of having information at the narrow frequency range, we can obtain interesting benefits, such as, for example, the requirement of a very low size of the sample or material under test, which is an interesting asset when the availability of the sample is limited, as it is the usual case in biomedical applications, and also the capability of making non-invasive measurements, making measurements of the permittivity and therefore of the composition of the medium without direct touch direct touching the material. So let's see how it works. Here we can see a very simplified model of a microwave resonator that can be modeled with a simple RLC circuit, either in series, either in parallel. Here we can see the model in parallel. If we analyze the input impedance or input admittance in this case, we can easily see that it has a real part due to the resistance and then an imaginary part with two contributions. A positive contribution to the imaginary part due to the capacitance and a negative contribution to the imaginary part due to the inductance. Both contributions indeed depend on the angular frequency, and this means that we can find one frequency that will make the positive contribution to the imaginary part equal the negative contribution to the imaginary part. That is, omega times C equals 1 over omega times L. At this frequency, both parts, both contributions to the imaginary part will compensate and the imaginary part will be 0, which means that the input admittance will be purely real, which indeed means that the input impedance will have the minimum value in its modulus. We can compute this value and we can compute it for different frequencies, and we can plot it and we can see how at the resonance frequency the modulus or absolute value of the input admittance is minimum, and this value rises as long as we move towards higher or lower frequencies. Well, this frequency, the resonance frequency, is defined in terms of the capacitance and the inductance. And we can define other metrics from the resonant peak in order to characterize the behavior of this resonator, such as the bandwidth, the minimum losses, or the quality factor. All these parameters will be again defined in terms of the inductance and the capacitance. So what happens if we analyze this with a more realistic model, such as, for example, transmission line models? We can have a transmission line resonator, such as an open-circuited lambda over 2 transmission line resonator, or short-circuited transmission line lambda over 4 resonator, and any other models. In this case, we have the same behavior, but we no longer have a concentrated capacitance and a concentrated inductance at a certain point, but now we have distributed capacitance and distributed inductance throughout the line. And their values depend on the permittivity of the substrate and on the permittivity of the materials in the surroundings, which means that the final parameters of our resonator in this transmission line model, the input impedance, the propagation and attenuation constants, and so on, will be expressed as a function of the overall permittivity of the effective permittivity, which is a combination of the permittivity of the substrate and the combination of the permittivity of the materials in the surroundings. So if we place the material we want to measure in the surroundings, the changes in the permittivity of this material will be seen as changes in the parameters of the resonator, and it will be seen as changes in the response of the resonator, such as changes in the resonance frequency or quality factor. So to sum up, at microwave frequencies, we have very reduced sizes of the material under test or samples, and we know that the dielectric relaxation processes of water and by extension of most biological systems are covered within the microwave range. And this is why we can propose that microwave technology allows us to investigate the effects of dissolved species on such relaxations. This means that we can use microwave instruments to analyze the composition inside biological systems, for example, inside the body, without entering into the body. For example, we can analyze the composition of a certain tissue, the presence of a certain element inside the body, or we can analyze the concentration of a certain element in blood without extracting a drop of blood. To finish with this part, here we can see the full wave model again compared to the simple circuit model. For the full wave model, we can see how the electric field lines travel through the substrate, but also they get out of the line, they get out of the circuit, they travel through the upper space, and they get back to the circuit. In this very simplified model, just for the example, we have included a sample holder, a container, and a liquid to be measured inside the container. And we can see how the electric field lines travel through the walls of the sample holder, they travel through the liquid, and then they travel back to the resonator. As the electric field is traveling through the liquid, the transmission parameter of the sensor will be affected by the properties of the liquid, which means that the final parameters, the final indicators from the response of the sensor, the resonance frequency and the allowed qualifier will no longer be a function of a certain capacitance, of a certain inductance, but they will be a function of the permittivity of the sample, of the properties of the sample. Please note that in this example, the liquid is not touching the sensor. There is the bottom of the container in the middle, and it could be the skin, for example, in a non-invasive biomedical application. So this is the end of part 1 with the basic theory of this measurement approach, and in part 2 we will review some practical aspects for real implementation of these instruments.